So, last week we discussed some basic properties of sensors. We discussed how to get accuracy, how to measure a steady state response of some kind of sensor. And at the end we have been discussing some basic information about uncertainties of measurement. And since we have completed the task on the lab class, I don't think we need to go through the last three slides from the last week's presentation, because it was already done on the lab class which we had last week. So today we'll go on with some more properties of sensors. First, say we'll describe the basic ones, and then we'll get directly into some specific types of sensors, which should be temperature sensors. So today we'll discuss the properties of sensors in a dynamic state, so dynamic response of any kind of sensor. Last week we have discussed steady state properties of sensors. So last week we discussed something similar to that. We had some input of the sensor, and we had some output of the sensor. And we were plotting some characteristic like that. So for example, today we will be talking about temperature sensor. The first one I will tell you will be PD100 temperature sensor. So the steady state characteristic for this kind of sensor is the dependence of electrical resistance on the output on temperature on the input. So this was the steady state response. And I told you that it's important that this response is in steady state. It means that you can plot this dependence only if you have a constant input and constant output. But there are specific applications where you need to measure not only the steady state response, but where you need to measure also some response as a function of time. In other words, how is the output of the sensor changing if I change the input, and what is the function describing this output function? So we'll basically today work only with this dynamic sensor properties. Before we begin, just a quick reminder, for every lecture there are some bonus questions that you can do and gain some bonus points. You can find the bonus test on those pages. The bonus test for lecture number 1 for last week's lecture is already closed, but there is a bonus test for today's lecture. It's open from today 9 a.m. until next week Wednesday midnight. So you can gain some bonus points. And a second reminder, I told you that already on last week's lecture and the lab class as well. There will be a safety briefing and test, and my colleague has changed the time. It should have been at 2 p.m. but he changed it to 4 p.m. So this week, so next week, it's March 6th, Friday, and you have to go to this briefing and pass the security test in order to work in class. Without this security briefing and test, you cannot continue in the lab classes. The test will be in lab F2-108, which is in the whole laboratories. If you look out of the window, you see the small buildings. And we are currently somewhere here, so we need to go all the way through the labs. And here on the left side of the corridor, there's lab 108 and do the test. Okay, so now let's start with the transient response. The question for today will be, how is the sensor behaving if I do this? I have time, and I will be watching the output of the sensor. We will do this experiment with the temperature sensor, but it can be any kind of sensor. So what have steady state, temperature T1, and I know this temperature is constant. So it's temperature. I will change the temperature somehow. For example, I will have this sensor placed in a tank with cold water, and here I will have a different tank with a different water temperature. So here there will be temperature T2. And now the question is, what will happen at minute? I will assume that I'm able to make a very fast response or a very fast change. So I know that the input will change instantaneously from temperature T1 into temperature T2. Now the question is, how will the sensor output look like? Will it be like that, or will it be like that, or will it be like that, whatever you can imagine. So now we will make an experiment. The output function will be called transient response, and it will be a function of time. So it will be a description of this curve that we will have at the end. So how will the experiment look like? We'll have two tanks with water. This is my tank with cold water. This is my tank with hot water. And this is my temperature sensor. Right now, the sensor is placed in the cold water, so that I have constant temperature on the in. I will take this sensor and move it into hot water. We will watch the output of the sensor, and we will plot the response. So let's do it. Now what you see is the input of the sensor. It's scanning every second the electrical stance of my temperature sensor. And now I will make a transient response. So let's try to see what will happen. I will put that into the wall. Now everything is set on the scale. Okay, again, some problem. Yeah, so as usual, there is some problem with the machine. Okay, so again the experiment was not successful. Let's try it again. Just try it on my computer here to see what happens. Okay, we will waste time on it. I will just plot you the response that we should have from the output. So we should see on the output of the device is a curve looking like that. And there is a defined function that describes this output. It's an exponential event. So every time you make a transient response, you will obtain an exponential event. Sometimes, for some systems, it will look simple like that. It will be first order exponential, first order differential equation. Sometimes it will be more complicated. We'll stick with the easiest example, which is the first order differential equation. In the general case, every system can be described by an n-order differential equation. So if you know the coefficients of this differential equation, then you can make a mathematical model of the system, and then you can say, okay, I know it will take some time before I reach steady state, or it will take longer, and so on. So this is the basic description, the general description of any system, also any kind of sensor. It is an n-order differential equation, which is more complicated to solve. So if you make some models, we typically assume that we use only a first order or a second order differential equations. So only some simple approximation of the real world. Although we know that the real description is more complicated, then we use only first or second order differential equation. So we'll start with the first order differential equation, and we'll examine the properties of this response. What can we see from this response that we can either measure or we can calculate it mathematically from the differential equation if we know that. So let's take the first order differential equation. It has only a first derivative. This is the typical form. A1, A0 are some coefficients. Here you have y is output and x is input. You can of course have some coefficient b and b input as well. It's not very common for general receive. So now if you take this equation and divide that by a0, you will have a0 over a1 over a0, and here you will have 1 over a0. What is important is that the term a1 over a0 will be some constant value, and it will be the most important parameter of any dynamical system that you can have. This parameter is called the time constant, and time constant is saying us how fast the system is. So in other words, how long it will take before I have reached temperature T2. So how will this curve look like? If the time constant is shorter, you will see something like that. If time constant is longer, you will see something like this. So this is really the most important parameter of any dynamical system. And it will be also your task during one or two lab experiments to measure this time constant. Why is time constant important? If you look at this chart, we have the input signal, which was a step function. So I immediately changed temperature from T1 to T0 to T2. But the output of the sensor was slow. So it means that if the time constant is long, the sensor cannot react to fast changes on the input. So there is a relation between the time constant of the sensor and between the speed that you can use for measuring any value. So not only that if you buy a sensor, you need to know in what range you want to measure, with what accuracy, but you also need to know how fast you want to measure. If you require every one sample for 10 minutes, then it's completely okay to choose a sensor with a long time constant. But if you select some high-speed experiment where you want to sample the value every 10 milliseconds, then you cannot choose a sensor with a time constant of 1 second, because it will not be able to react fast for the input. So that's one critical parameter. time constant that you can read from the description or that you can measure with some experiment. The second critical parameter would be this one over A0. And we will also measure this during our lab classes. Why? If you look at this differential equation, I have the form I get. So let's say this is time constant times derivative as y equals some y over A0 times x. This parameter will describe us the behavior of the system in steady state. Not only in steady state, but mostly in steady state. Why? What is the value of this part in steady state? 0, yes. So this is 0, and we have y equals some constant value times c. So this is exactly the description of this steady state characteristic. So this would be the sensitivity. I told you last week that sensitivity is basically the slope of this curve that we have, and this is the sensitivity when we describe the differential equation. So this describes us the behavior in steady state of the system. It's clear that it also influences the behavior in the transient response. We will just examine its behavior in steady state. So now, what can we tell about the system? If we know the time constant and if we know the sensitivity. Let's examine the solution of the differential equation. From mathematics, we should know that if you have first order differential equations with constant coefficients, then the solution is an exponential function, and that the output is a function of time, and it has this form. There is some constant, and this constant describes you the value of steady state. And there is an exponential part, and here you have the time constant. So it means that there is a simple description of this curve. And it's valid for all systems that are described by the first order differential equation. So here in this description we have some steady state value of the output, and here we have some time constant. Now, last week we have also been talking about dynamic error. What was the dynamic error? Dynamic error was the difference between the correct value and between the measured value at the same time. So if you look again at this chart, the input was step function. So I know that the correct temperature was here T1, and from this time, from time 0, it was T2. So now for me, T2 and T1 are the correct values. I have measured something else. Let's say that I need to look at this time. And at this time, the sensor output is different. So, the correct value is T2, and the measured value is some other temperature. So this value is the dynamic error. And as I'm reaching T2, the dynamic error is getting smaller. So the dynamic error in steady state is 0. You can substitute that in the solution of the differential equation, and you can say, okay, the dynamic error is getting smaller and smaller, and you will see that the dynamic error is also an exponential function. So the dynamic error is the highest for time 0 and is the smallest for steady state. If you look for this equation, for all time t is the value of dynamic error 0. In other words, how long does it take until I reach steady state. For the value for t, you need to substitute here so that this is 0. If you look for the value here t, you will find out that it's infinity. So only in time infinity you will have a new steady state. Now that's very practical because if I make this experiment, I need to wait a very long time before I reach steady state. So now the practical question is, how long do I need to wait in reality before I have something that's close to steady state? So what do you think? How long do I need to wait? Will it depend on the time constant? Probably it will depend on the time constant because the higher the time constant, the slower the response, and I will need to wait longer. The faster the response, the sooner I will be into something that's new steady state. So if you look at this picture, here there is a transient response, sensor input is this curve, sensor output is this exponential. And if you analyze the equation describing dynamic error, you can find out that if I wait one time constant, so here you have 1 over 1, you will be only within about 63% of the new steady state value. So if my steady state value was this, if I wait only one time constant, I will be only within 63%. If I wait longer, if I wait at least 3 times time constant, then I will be approximately within 95% of the steady state value. And if I wait at least 5 times constants, then I will be approximately within 99% of the steady state. So it means that, for example, my sensor has a time constant of 1 minute. If I want to be within 99% of the new steady state value, I will have to wait about 5 times time constant, so 5 minutes. If I am satisfied with lower precision, within 95% of the new steady state value, I can wait only 3 time constants. So if you want to make some dynamic readings from your application, you need to know time constant from the sensor. Either you read that from some data sheet, or you can measure it with some experiment, and then you will know, okay, time constant is 1 minute, and I have to wait 5 minutes before I'm satisfied with 99%. So, we have basically discussed this and that. So now how to make an experiment, how to measure this time constant. If you have some graphical, it's not always you will have some differential equation describing your system. So it's a relatively easy to do this experiment with temperature sensors. You do the same thing like I tried to do here. You have 2 tanks. So temperature, you move the sensor from one tank to another, and then you measure the response. How can you determine the time constant if you have just one? So there are several ways that you can use. One way is to say, okay, this is the initial steady state, let's say 0, and this is the new steady state, let's say 100%. We know that it takes some time before I am reaching 63%. This time is equal to the time constant. So I can say, okay, 63%, so now here is 63.2%. How long did it take from the start until 63%? And this is time constant. So let's one divide this into 63% and say, okay, this is time constant. There is a different way as well. It's a property of the exponential function that I can make a tangent of this function at any point. So let's say I will make a tangent at the origin. So tangent here at this point and 0. And this time from 0 until I have reached steady state value is also a time constant. This works for all points. So let's say I make a tangent here and choose this point as the initial point. I make a tangent, and here I should have the same value, the same time constant. So it's quite easy to do this graphical analysis if you have much data, so it's not that difficult to measure the time constant for temperature sensors. Sometimes there is a problem how to make this step change fast enough, because for some variables it's not possible. We can change voltage quickly, we can change temperature by moving the sensor, but how do you want to change, for example, humidity, or how do you want to change pressure and so on. So for some variables it's more difficult than for the other. So once again, let me repeat, how long does it take until average steady state? Well, it takes infinite time, but in practical terms, if I weigh 5 time constants, I'm within 99%. If I weigh only 3 time constants, I'm within 95%. And if I weigh only 1 time constant, I'm within 63% of the user's value. Now, how about some more complicated description? We know that the general description is an nth-order differential equation. We discussed on the first order system, but in some cases we cannot simply describe the system by a first-order differential equation because it does not correspond very well to reality. So in those cases, we can say, okay, we choose something more complicated, and we can describe the sensor with some more complicated equation, which will be the second-order differential equation. We will not go through the analysis. I hope you know that from mathematics. I will just show you the solution in a graphical form. We know that there are 3 possibilities for the solution of such a differential equation, and that this is based on the roots of this differential equation. So, what can be on the output? There are 3 possibilities. If the roots of the differential equations are real and different, we will have a response in this form. Okay. Again, it's an exponential function, but there are 2 functions that are multiplied together. Second possibility is a little bit faster, and it is when you have real roots, but they are equal. And the third possibility is where you have complex roots, and you will have them at certain response. Now the difference, if you note, there is an immediately visible difference between the first order and the second order system. Where is it? What is different in this response? What? This time. Yes, exactly. So if I show you the response of the first order system, say T and Y, the first first order system starts to react at the same moment where you make that change. But the second order system has here some delay, and typically it takes longer for the same system to react. So there is an immediate difference at the origin. So we'll make an analysis. When you will be doing a lab experiment with temperature sensors, which will be approximately 3 weeks, all the response that we will measure will be similar to the second order system. So there will be some delay before the sensor will give you an output. But in order to simplify the analysis, we will assume that this is still a first order system. So this is a real simplification. On the measured data, you will see that it looks like that takes some time, then it reacts. And of course, so that's the transient response. It's not always possible to create such a fast change in the input. For example, you have a large tank, you cannot move the sensor from one tank into another, or you are interested in the transient response as the system as a whole. So you cannot make this step change on the input. So how to get the time constant? We can measure the response of such a system, but we will now modify it. It will no longer be fast change, but it will be a ramp response. So it means that we will slowly increase the input value, and we will watch what is happening on the output. Again, an example with this water tanks. Let's say this will be temperature of the water, this is time, and I will start from some temperature, let's say 20 centigrades. This will be 20 centigrades, and here the temperature of the water will be constant, and I will turn some heater on in the water. So the temperature of the water will slowly increase. That's my input. And now I'm looking for the output. So if I will assume the first order system, then there will be an immediate change on the output. The sensor has some time constant, so it cannot react instantaneously on the input. So there will be something like that. So this is the first order ramp response. Now if you describe this mathematically, you can see that okay, input is time, and this W is constant describing the slope to this input value, and the output, you see again, is an exponential function. So we can analyze simply what is the time constant of this system. Because here, if you make again an unband in this area where this is parallel to the input value, then this is time constant. So we can analyze again graphically how fast our system is without the necessity of changing the input steps. If it's a more complicated description, like second order system, you will again see some delay before the output will react immediately to change, and a second order system, and you leave a delay here, and you see something like that. So again, you can see immediately if your system behaves like the first order or like a higher order system. Now the question is, what about dynamic error? Where is dynamic error? Well, we know dynamic error is the difference between the real value, which is this input, and between the measured value. So I know that the curve which is this line, the measured value is this line. So there is always some difference, and the smallest difference is when you start. So in this case, the dynamic error is minimum at time 0, and then here you have some constant value. So that's different when you compare the round response and the transient response. For the transient response, we have dynamic error getting smaller and smaller. Here, the error is approaching some constant value, and it remains a constant value. Now, how long do I need to wait until I have reached, say, maybe a steady state as well? So, how long do I need to wait until this dynamic error is a constant value? What do you think? Does it depend again on the value of time constant? Probably it does. So, how long do I need to wait? It's the same like for the transient response. If I made a transient response, step change, how long was it necessary to wait until I was within 99%?
5 times.
Yes, five times. It's the same here. So if you want to wait until the transient fades within 99%, then you really need to wait about 5 times time constant. Any questions? With dynamics? Everything is clear? Okay, so we just briefly stop at some basic electronic circuits, because if you have a sensor, you need to connect the sensor to a control system, and we will need some basic circuits that will allow us the connection of sensor and control system. The whole system will be composed of several, say, electronic boards. We will have the sensor itself. We will have a medium, some physical property, it could be temperature, it could be humidity, it could be whatever value you can imagine. And the sensor transfers this physical property into some output signal. In my case here, in what you've seen so far, it was electrical resistance, for example. But in some cases, it's voltage, it's current, it's capacity, and so on. And in order to interconnect different systems, we prefer either some voltage or current signals. So we will need some basic electronics that takes this transducer output and transfers this to some standard output signal. There are some standard signals, either voltage, current, that you will find all over the world. If you take a look on this table, we'll start with voltage signal. How does it work? Let's say I know the range of my sensor. Let's assume I will have a simple sensor for temperature that will be measuring from 0 to 100 centigrades. And I will say if temperature is 0, voltage will be 0 volts. If temperature is 100 centigrades, voltage will be 10 volts. So there will be a linear relation between the temperature and between the output voltage. For the other ranges, it's working in the same way. I can say, okay, if temperature is 0, voltage will be minus 10 volts, and if temperature is 100 centigrade, voltage will be plus 10 volts. So then, in the data sheet of the sensor and the corresponding electronics, you have to find this relation. It works in a similar way with current. I can say, if temperature is 0 centigrade, then current is 4 milliamps. If temperature is 100 centigrade, then current will be 20 milliamps. So the values that you see in the table are the most common standard signals used for industrial applications. So from 0 to 10 volts, from minus 10 to 10, from 0 to 5, and from minus 5 to 5. But from those four, the most common one is from 0 to 10 volts. And the current is from 0 to 20 milliamperes, and the more common one is from 4 to 20 milliamperes. So we'll need some circuit that takes the value from the sensor and transfers this to some standard signal. It can be temperature, it can be pressure, it can be humidity, whatever you can imagine. The reason why we do this is that I want some standard control system and I want to connect this with some other manufacturer that is doing the sensor. So now we'll take a look at the properties of voltage and current signals. What are the advantages and what are the disadvantages of both outputs? So let's start with the simple voltage output. It's quite easy to measure voltage. So I have a sensor that gives me voltage proportional to some physical property. Between the sensor and between control system, which can be a simple voltmeter, it can be a computer system, whatever you can imagine, there will be some wires. And wires have electrical resistance. So there will be two resistances. Here, this is the resistance of the wire, and this is the input resistance of the voltmeter. If I measure voltage with the voltmeter, and here I have some non-zero value of electrical resistance, it means that the voltage on the sensor will not be the same as the voltage that I measure. Because here on this wires I will have some voltage. So the longer the wire will be, the higher the voltage drop, and the longer the voltage that I measure. So the actual value that you will measure will be dependent on the electrical resistance of the wire. That's one problem with voltage outputs. Second problem is what will happen with noise. You will have a sensor of temperature. Between the sensor and between the voltmeter, you will have 100 meters of cable, and this will go along some electrical machines. You will have pumps and so on. So when those machines will run, they will produce some noise, and this noise will induce into the wire. And again, the longer, the higher the probability that it will pick up noise. So there is a second problem with noise for voltage output. So the voltage signal is good in environments where you do not assume you have any noise sources like electrical machines, electrical pumps and fans and so on. Or if the distance between the sensor and the meter gauge is relatively short. So the voltage output is used, for example, in a building environment control. So if and standard input is from 0 to 10 volts. But for industrial systems, the better solution is to use a current output. Why? If I have a sensor like that, and I measure current coming from the sensor, what is happening in the loop? Again, there are some wires between the sensor and between the FA meter in this case, or any control system. And I measure current. Current, this whole loop, is the same. So there is no drop. I will not measure different current at this point, different current at this point, and different current at that point. So that's one advantage of the current output. You always measure the same value of current in the whole loop. Second advantage is that the current output is less successful, it has a higher immunity against noise. So it means that if something will induce, some voltage will be induced into those two wires, the current will still stay the same unless it's like high energy. So current output has higher immunity against noise. There is also one disadvantage. It is limited in the length that you can connect between the sensor and between the output, between the why? Well, how do I achieve some current in the loop? If I want to push some current through the loop, I need to change voltage on the output. So typically, there is a current controller built into the sensor, and it maintains a constant current. If I use longer wires, I need to have a higher output voltage if I want to have a constant current. So the longer the wire, the higher the voltage will be output of the sensor. And for security reasons, I cannot have the voltage to be output too high. So it means that there is a limit in output voltage, and there will be a limit in the length of the wires. So typically, the load that you can connect to a current output sensor is 600 ohms. And as we typically use about 100 ohms in the load to sense the current, this gives us 500 ohms for the wire. So then it's up to you to select the wire with some low enough resistance so that it is within those limits. So remember that the current signal is has a higher immunity against noise. In the industrial systems, it is the most common type of signal that you can measure and find. There is a different advantage to this current signal. If I take the range from 4 to 20 milliamperes, this gives me an easy way how to detect if there is a problem with the loop. Because I know that the minimum value of current that I measure should be 4 milliamperes. If there will be some broken wiring between that, the current will drop to 0. So I can immediately detect that there is a problem with the connection. So for all those reasons, the most common type of sensor output that you will find in the industry is from 4 to 20 milliamperes. So it's a standard value. Now, how to produce this voltage and current outputs? How do I take the value from the sensor and transfer this to the voltage or current? We will discuss only one connection. It's a bridge connection. Have you heard about a Winston Bridge? Okay, so we're going to use a Winston Bridge for this function. So, if you look on the bridge from the power supply side, the bridge can be supplied either by DC voltage, AC voltage, or some impulse voltage. So this will give us a DC bridge, an AC bridge, and an impulse bridge. We will discuss only the first one, the DC bridges. So in the DC bridge, we power this DC bridge with a DC voltage, and the property that the sensor is changing has to be a DC property. So it means it has to be electrical resistance. So if your sensor is changing electrical resistance, then you should take a DC bridge. If it's changing an AC property, like capacity or inductivity, you have to take an AC bridge. The connection is similar to the DC bridge. We will not discuss AC bridges. So when the sensor will change capacity or inductivity, you need to use an AC bridge. The impulse bridges are something that we power the impulse bridge with a rectangular pulses of voltage. And we can evaluate all three. We can evaluate resistance, capacity, or inductivity. The reason why we are using impulse bridges is that it's easier to amplify AC signals. So we can use amplifiers on the voltage output from the bridge. But again, we will just discuss DC bridges. So that's from the point of view of power supply voltage. There is a second way how to look on the bridge. I can take a look on the output of the bridge and on the way how I change the setting of the bridge. So I can either change the values in the bridge, and I can keep changing until I detect zero voltage or current on the output. So I'm looking for some setting of the bridge, and I'm changing it until I have zero. This will be called a balance bridge. So a balance bridge will have some elements that I will change, and I'm looking for zero. This obviously takes some time before I will be able to balance the bridge. So balance bridges are used in labs where you don't really care about how long it will take. But the big advantage of this balance bridge is that you don't need to care about linearity. Zero is zero. I don't care if it's linear or non-linear. On the other hand, for industrial systems, you need fast reading. You don't want to set any knobs on the bridge. So you will have to read directly the voltage or current from the bridge. So you will read some value. You will not balance anything on the bridge. So this will be called an unbalanced bridge. We will read directly the voltage or current. The disadvantage will be that the response of the bridge is nonlinear. The more unbalanced the bridge is, the bigger the nonlinearity. So there is a trade-off. Can I take some time to balance the bridge? Then I don't have any problem with linearity. Or do I need a fast reading and I will have some nonlinearity? So in our labs, we typically use balanced bridges. Industrial systems use typically unbalanced bridges. Okay, so that's basically what I have to do right now. So balanced bridges will give you precise results. 4 resistors. I assume it's a DC bridge. So R1, R2, R3, R4. I need some power supply, some power supply voltage with some of those terminals, and I will be voltmeter some voltage on the output. So I will just simply break it on this figure so that I can show you what we can do with the bridge. Really the power supply, it's a DC voltage, and here in the output I will have some meter will show me output. Well, I will analyze the behavior of this circuit. You can recalculate this circuit and do something that's easy. Let's call those terminals C and D. So I will look from those terminals and I will try to simplify this whole connection. Take terminal C and terminal D. You can redraw this circuit with very simple internal schematics. You can say, I look at terminals C and D. And I don't care about the functionality, I care only about similar electrical behavior. So according to theory, I can say there is some internal resistor and there is some voltage source. That's all. And on the output, I will have voltmeter. Well, voltmeter basically is also a resistor. It's a coil in DC circuit, it's a resistor. So I will have here the voltmeter resistance RV. And we will be interested in the current flowing out from those terminals. So, according to Ohm's law, current will be voltage divided by RK plus R. 0 over RK plus RB. So what does this equation mean? It means that the current that I measure depends not only on the internal properties of the bridge, but it depends also on the instrument I use to measure the output. So for a bridge correction, it's quite important to select a good voltmeter with some known value of internal resistance. Because then you have different readings for different voltmeters. That's a good. So the result really depends on the value of what instrument you use. So that's one problem. Second problem is that the current on the output will be nonlinear. If you analyze what is behind RK here, you will find out that there is a complicated connection of R1, R2, and electric resistors. And if you really analyze this equation, you will get some huge equation. I just showed you the equation. You need to remember that just will take a look at its properties. So this is the result. The current from the bridge depends on the power supply voltage and depends on all this complicated equation. So the output will be quite nonlinear. And if I balance the bridge, I want current 0. So when will this part be 0? Either if V0 is 0, then it doesn't make any sense to have a bridge. Or if this part is 0. So if you change the values of those resistors until you meet the equation is written here, or the same equation. In other words, until you meet the conditional balance, then you will have output 0. So the goal of balancing the bridge is to change the setting of the bridge until I have fulfilled this equation. Then the output will be 0. So that's the balanced bridge. And an unbalanced bridge will measure directly the voltage on the bridge output. So when the lamp will get longer, I have to set the elements until I have 0, and the diode will just make the voltage. But for this equation, you will see that there is a collinear dependence between the values from the sensor and the value from the bridge output. So now, what options do we have if we want to unbalance the bridge? Let's say this is my bridge. I have 4 resistors. So where is the sensor? Where do I have resistance? Where will be the sensor? Well, we will have the two options. We start with the simplest value, simplest solution. We will have one sensor. Let's place a sensor instead of R1. So R1 will not be a fixed resistor, it will be a temperature sensor, for example. So this value will change with temperature. If you have one sensor connected in the bridge, we will call that a one-quarter bridge. So we have one-quarter bridge. We are changing the input and we are looking on the output. If my connection will have some sensitivity, as we could calculate that, it will be a constant value. So for one sensor, we have one quarter bridge and we have some sensitivity. If I take 2 sensors and 2 sensors can be placed in 2 ways. We can have a sensor like here and here. Remember the conditional balance. Conditional balance for this kind of bridge was R1 times R4 equals to R2 times R3. So if I want to unbalance the bridge, here for one-quarter bridge, I have chosen R1. So let's say I have increased R1. I have unbalanced the bridge and I have measured the voltage. Now I have 2 sensors. So I can have either R1 and R4. So I unbalance the bridge here and here. It will give me higher voltage in the output. Or I can unbalance the bridge with R2 and R3, which will again unbalance the bridge in the same way. I will measure the output. So if my sensor is increasing its value, increasing it, for example, increasing electrical resistance with temperature, and the second sensor is doing the same, I have to connect them on the same side of the equation balance. So that's what's shown here on the left page. In some cases, I have two sensors, but one sensor is increasing with increasing input, and the second sensor is decreasing with increasing input. Typical example is a force sensor, strain gauge. You have a strain gauge on top of the beam, you bend the beam down, so this upper strain gauge is measuring tension, and if you have a second strain gauge on the bottom, you bend the beam down and it measures compression. So that's a typical example where with increasing input, one sensor is increasing and the second sensor is decreasing. So in this case, I need to rearrange the connection. Let's say R1 will be increasing with increasing input, and R2 will be decreasing with increasing input. So now R1 is increasing and R2 is decreasing. So if this is the case, I need to have the sensors in this place if I want to analyze it, or in this place R3, R4. So there's a half range because we use two sensors. If you compare the sensitivity between a one half range and a 1/4 range, you will find out that the sensitivity of one half range is doubled over the sensitivity of 1/4 range. That's the reason why we do this connection. We have higher sensitivity. Now, what about if I want even higher sensitivity and I can use more sensors? So, if you use 4 sensors in a full bridge connection, then you will have 4 times the sensitivity of 1/4 bridge. Here it assumes that 2 sensors are increasing with increasing input, and 2 sensors are decreasing with increasing input. Again, a typical connection where this is used is 4 sensors. So the strain gauges, every weight that you have at home or in the industry will use full bridge of strain gauges. So 2 will measure tension, 2 will measure compression. So note that this one is plus minus delta R, this one is plus minus delta R as well. It's this resistors, same side of the equation, and the 2 others on the other side are minus plus delta R. So they are measuring in a different direction than the sensors placed. Without this arrangement, you cannot have a full bridge connection if you have 4 sensors that change in the same direction with the input. Questions? Okay, no questions. So now we'll make use of the bridge connection for some real sensors. And as everything is influenced by temperature, we will start with temperature sensors. And today we'll discuss the most common type of sensor, which is called the RTD. The RTD is a kind of sensor that changes electrical resistance with temperature. So the output of the sensor will be electrical resistance, the input is temperature. So the RTD will give you different values of electrical resistance as a function of temperature. Then you can take this RTD and connect it to a bridge if you want a voltage or current. There is some defined dependence between temperature and electrical resistance. find two equations. One equation is valid for smaller ranges of temperatures. So in a normal temperature range from about 0 to 100 centigrades, we can describe that electrical resistance depends on some initial resistance and on the temperature coefficient of resistance. And temperature coefficient of resistance is defined as the change of electrical resistance between 0 and 100 centigrades. So this is valid in the smaller ranges, let's say about 100 centigrades or 0 to 100 centigrades. If you want some higher ranges or some higher precisions, the equation gets more complicated. So we can still see one part of this equation here. R0, 1 plus some coefficients times temperature. But the other terms are small for the small range. But if you have a bigger range, then this part can be significant. So if you are working with a small temperature ranges, you can easily use this form of equation. But if you want some higher ranges, 0 to 800 centigrades, for example, you need to use a more complicated description if you want to make a decision. So now, what materials do we use for RTDs? There are three metals that are typically used in the industry to create an RTD. One will be platinum. That will be the best one, but the most expensive. The second will be nickel, less expensive, but much lower precision. And the third that we will discuss will be copper. Even less expensive than nickel, but really bad precision, really bad stability. So we'll start with the comparison of those three metals based on the temperature coefficient of resistance. What does it mean, temperature coefficient of resistance? If I will plot the dependence of electrical resistance on temperature, and if I say, okay, it's a linear dependence, then the temperature coefficient of resistance is nothing else than sensitivity. It is describing me how is the output of my sensor changing if I changing. So the temperature coefficient of resistance, say the higher the better for us, because it will give us higher sensitivity. So let's compare those three metals. Here is the element, platinum, nickel, copper. The first column is the temperature coefficient of resistance, and the third column is resistivity. It will tell me how big is the electrical resistance on the wire with some given length of some given cross section. So let's start with platinum, 3.92. If you just look on the code, you see okay, 6.17. You will see that it has a higher sensitivity. You'll see grades true, but with some limited range on it. Copper is approximately the same temperature coefficient of resistance like platinum. And it's less expensive. If you compare resistivity, here you have 9.81. For copper, we have 1.1. So it means that if you have a platinum wire and a copper wire with the same cross section, with the same length, the copper wire will have approximately 10 times lower electrical resistance. It also means that if you want to build a sensor with some defined electrical resistance, which has standard value of 100 ohms, then the copper sensor would have to be 10 times bigger. So platinum sensor will be that big, and copper sensor will be that also space limitation. There are many other limitations why cathode is not typically used for sensors. The nickel has approximately the same electrical resistivity like copper, so the sensor size would be the same. We'll discuss the nickel and copper sensors a little bit later. Now we'll discuss the platinum sensor. So platinum sensor for temperature is the most common type of sensor that you will find in the industry. There are several reasons. Platinum is a very stable metal. It does not change really much with time. With some chemical properties and so on. So it's very stable. The second reason is that it has relatively high resistivity. So it means that I can create a temperature sensor that will have high electrical resistance. It will need low current, but it will have higher sensitivity. And probably the biggest advantage of platinum sensors is that they do not require any additional calibration. So it means I can take a sensor for temperature, it's called a PT100, and I can replace the sensor in my application without recalibrating everything. The disadvantage of platinum sensors is that it's really expensive. So if you are able to buy a platinum sensor, that is the best solution for many applications. And the standard name of the platinum sensor or of an RTD is composed of the letters PT, meaning platinum, and a number. And this number means what is electrical resistance of the sensor for 0 centigrades. The most common sensor is called a PT100. So it means it's a platinum sensor. It has electrical resistivity precisely 100 ohms for 0 centigrades. How does it look like? Here I have an example, the PT100. There are several ways to encapsulate that. Just talk about this. This is the PT100. So inside there is a platinum wire, and on the output we measure electrical resistance. A different version is shown here. It's a little bit later. It's called the thin film version. It's a platinum based on some chemical. We'll see also more of those sensors in the lab. There is a second version of a PT sensor that is also common, but less common than the PT100. It's called the PT1000. So following the same scheme, it means that it has precisely 1,000 ohms for 0 centigrades. Those two sensors are the most common sensors that you will find for temperature in the industry. How is it with linearity? Well, in smaller ranges, we can say that the PT100 is a linear sensor. So if you use the sensor from 0 to 100 centigrades, it is linear, more or less. It's on small level. But if you use this in a bigger range, PT100 can easily be used up to 600 or 800 centigrades. Then it's non-linear. If you look at the description of the equation here, the values of the coefficients, you can see, okay, A is 3.9 10 minus 3, but those other coefficients are both 5 orders of magnitude smaller. So if temperature is small, then it's no problem to use just the first coefficient and to assume that this is the linear element. For bigger ranges, you have to use more triple efficiency. And if I assume a linear independence, I can define the sensitivity as a constant value. And we can say that the sensitivity of the PT100 is 0.39 ohms per centimeter. So if I will have 0 temperature, I will have precisely 100 ohms. If I will have 1 centigrade, I will have 100.39 ohms, and so on. The linearity or non-linearity can be judged from this chart. You can see bigger temperature ranges. It even looks non-linear, but if you take really only a small range, it is. Now, how about precision? What can we expect from a PT100? It depends on the purity of the platinum that is used in the sensor. There are 2 classes of accuracy defined for the PT100. The class A gives you about 0.15 plus is below 0.02 temperature. So it's more accurate than class B, which has about double the interval where you can expect it. To give you an estimate of precision, so let's take 0 centigrades. So 0 centigrades means 100 ohms. This is plus minus 0.06 ohms, and this means plus minus 0.15 centigrades. If you measure 600 centigrades, then you can, for class A sensor, expect accuracy of 1.3 centigrades. For class B, you can have about 3 centigrades of accuracy, which is below 0.5%. So the PT100 sensor is a very precise sensor. It's also a very expensive sensor. The one that we will use on the lab class, it's approximately between 50 and 100 euros for a piece of sensor. So the one that we have here is the price. The range depends on the encapsulation of the platinum. So we will use something that's called a glass platinum sensor. How does it look like? It's a thin platinum wire mounted like a coil, and this is encapsulated in glass. It looks something like this. It's like a rod, as you can see directly the platinum wire inside. And due to the glass that is used here, it can be used up to 600 centigrades approximately. That's the maximum temperature used. For higher temperatures, you need to use ceramic version, the PT100. And ceramic version is also thin platinum wire. Now in ceramic you can see, and ceramics can work for higher temperatures than glass. So this ceramic version can be used up to 850 centigrades. Those are ceramic ones. The price is approximately the same, and we depends on the application. But in all cases, we have to protect the sensor from damage, from mechanical damage. So in all cases, we will not submerge the PT100 sensor directly into some tank with some material, but we will protect it with something that is called thermal. This is a thermal. This is a thermal as well. So we'll discuss thermal next week, but it's nothing other than a pipe closed at the end. The sensor is inside. So we will also discuss how is the thermal changing the properties of the sensor. It's clear that it will not change static properties, but it will very much change dynamic properties. Because it's clear that if I take a thermal well like that, a thin thermal well, it will take a shorter time for the heat to be transferred from the liquid to the sensor than if I take a thermal well like this. So thermal well will protect the sensor, but will make the time to start longer. So those are the two versions of BD100. And the third version is a thin-filled BD100. That's the one I showed you in the plastic bag. It looks like thin film of platinum on the ground holder. The advantage of this thin film version is that it's much cheaper because it uses less platinum than a ceramic or glass BD100. It is a little bit less precise than the BD100 typically used. It can be used approximately for the same temperatures, and also the size is very small. One I showed you is maybe 2 by 4 or 5 millimeters. So a thin film platinum sensor is typically used to measure surface temperatures on some object. It's not used to measure temperatures of liquids in tank and so on, but it's used for surface temperature readings. The price here is approximately what it was. So it's much less expensive than glass or ceramic versions. It's a little bit less precise. Any questions? Okay, no questions. So see you in the lab in 15 minutes. The one room